Hey everybody, it's David Townsend from the Net Academy. Welcome to this session where I'm going to be going through the basics of the TCP/IP networking stack. Obviously there's a lot of layers, there's a lot of information, there's a lot of protocols within these various different layers. Now, no human being is of course going to know every single protocol in detail for every single layer. For me, that's not humanly possible. So I'm not going to do that. What I'm going to do is basically cover the basics. What is the OSI stack, or what is the TCP/IP stack? What are the layers called? What kind of information do we see at those layers? And really start building on that layer 2 perspective. I'm going to move away from layer 3 for this video and a few others. I'm concentrating on layer 2, specifically VLANs, or virtual local area networks. After we've gone through the basics of the TCP/IP communication at layer 2, layer 3, layer 4, etc., I'm going to go on to VLANs and cover what are they, what do they do, what benefits do they do, why are they needed, and of course how to configure them on Juniper Junos devices. So let's get going. So let's start off with the basics. Let's start off with what does OSI actually stand for. OSI stands for Open Systems. I won't write the whole words out, they're quite long names, but Open System, well, letters I should say in words, Open Systems Interconnection. And there's actually 7 layers in the OSI stack. So we've got layer 7, which is right at the top, layer 6, layer 5, layer 4, layer 3, layer 2, and guess what, layer 1. Now each one of these layers in the OSI stack has a specific name. So when we talk about layer 1, we're actually referring to the physical layer. So whenever you hear someone talk about the physical layer, they're talking about layer 1. And the physical layer, it's really, from an IP perspective, it's really the medium of communication. Now that might be satellite, it might be radio, 5G, 4G, 3G, it might be Wi-Fi, Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, Wi-Fi 7 when that's actually standardized. It might be optics, so when we talk about core and aggregation distribution, especially on the uplinks, we're talking typically about optical wavelengths. We've got fiber to the home, fiber to the cabinet, fiber to the antenna. We basically talk about fiber optics, and we've still got the electrical cabling as well. And there's different methodologies of transporting the signal at layer 1, you know, ADSL, VDSL, etc. It's not my area of expertise, but all this really resides at that physical layer, or you might argue layer 1, 1.5. But really, layer 1 is the physical layer. And in terms of format, when it comes to how is the information actually represented at that layer, and this will make sense as I build up the layers. Here we're actually talking bits and bytes. So bits being either 0 or 1, 8 bits in a byte, and then you have X amount of bytes going to, well, 1,000 bytes going to kilobyte, 1,000 kilobytes go into a gigabyte, so on and so forth. And it goes up quite drastically from there. But that's layer 1. At layer 2, we've got our data link layer. And to carry on in terms of how the information is formatted, represented, shown, how we refer to that information at layer 2, here we're talking about frames. So when you hear someone talking about the data link layer, or talking about the Ethernet frame, you're talking about layer 2 communication. Now layer 2 communication is switch to switch, and that's very loose, really. It could be switch to multi-layer switch, but really it's layer 2 communication. We'll go into a bit more on that. You can see I've got some nodes in this lab, which we're going to go on to in just a bit. But Ethernet is a layer 2 protocol. It is a data link layer technology, which is really switch to switch. So when we've got our different hosts, as you can see here, host 4 and host 3 and host 2, they're using that physical layer, the electrics, the satellite, Wi-Fi, etc., to communicate through this, well, it's actually router, but through what would be a switch to get that layer 2 communication. Because when we talk about layer 2, we are talking about a local area network, or LAN. i.e. the hosts, the servers, the recipients, the participants in that network are local. They're in the same geographical area. And so Ethernet provides that data link layer technology through the use of an Ethernet frame. Now, when we go to layer 3, we are talking about the network layer. Now, this is often referred to as the IP layer, the Internet Protocol layer. This is the layer that I absolutely love. It's the layer that I've been studying into for quite a few years, and so have X amount of more experts out there. But it is the network layer. This is where IP, or Internet Protocol, actually exists. And this is a huge world, absolutely ginormous. And here we're talking about packets in terms of how that information is represented. So when we talk about IP, yes, we're talking about IGP, Internet Gateway Protocol. Within there, you've got different protocols like ospf, RIP, RIP-v2, from the Cisco world, EIGRP, BGP, whether it be interior BGP or exterior BGP. Those are all routing protocols. But then we've also got the way of addressing the IP packet, whether it be IPv4, which has been around for many, many years and should be no longer on the networks, but it is, or IPv6, which is the newer way of communication over IP networks. And these two types of communication at the IP layer 3, they do actually coexist with each other. So you can have IPv4 and IPv6 on the same network, but you've got some tunneling methodology, but won't go into that. But really, the layer 3 is the network layer, IP, the packets. At layer 4, we've then got our that's spelled incorrectly. It's spelled our transport layer. Now here is where we are actually referring to segments, i.e. segments of actual communication. So here we've actually got TCP or UDP. There are others, but these are really the more common methods of transporting that underlying application, delivering that service. TCP is referred to as a non-real-time delivery method because it carries so much more overhead than UDP, but it guarantees delivery. It's all done by sequence IDs and acknowledgements going back and forth, and there's checksums, etc. in there. And if a recipient doesn't get a particular sequence, he's not going to acknowledge that sequence back to the sender, and then the sender will know, well, they didn't acknowledge that particular sequence, so they must have lost it, or it's still in the network, or it's taken too long, maybe it's arrived out of order, let's send it again. So TCP is for non-real-time services. Now, if we put that into perspective as to why you would want that, that retransmission and that extra lag, because it does take longer. If you look at it for online banking, which obviously you want security for, but that's a separate topic, or if you're downloading an iTunes video, I use Apple, then you want to guarantee that that information is going to get from A to B. You're not going to be particularly impressed, are you, if you've bought a film for 10, 15, 20 pound and parts of it are missing? And that's where TCP comes in, because it guarantees that delivery from that server to that client. UDP, on the other hand, is for real-time services. It is far less overhead in terms of header information compared to TCP. TCP is at least 20 bytes of overhead, whereas if we actually compare that to UDP, it's only 8 bytes of overhead, so it's significantly less. And what that allows is a faster process of sending information but not having any acknowledgements actually coming back. However, it is for non-real-time services. So what is layer 5? Layer 5 is the session layer. Layer 6 is the presentation layer. Just going to write presentation here. And finally, up the top, we've got layer 7, which is that application layer. So what do the layers 7, 6 and 5 all have in terms of format? Here we're just really talking about data. So data being that service, which is that application that's been pushed. That might be online banking, real-time video, Skype, Teams, Outlook, emails, etc. I don't do a lot of these layers, but I just know those are the layers, and it's typically just data. I'm more layer 1 to layer 4, really focusing on layer 3. But that's the OS side stack. How does it actually refer to and compare to the TCP IP suite? Well, in terms of the layers, you still have 7 layers. In terms of the format of information, it's exactly the same. So at the physical layer, yeah, you've got different ways of transporting that information, but really it's still the physical layer, it's still bits and bytes. At layer 2, it's still frames. At layer 3, it's still packets, so on and so forth. However, the only real significant difference is for the TCP/IP stack, they refer to layer 2 and layer 1 as that network layer, just so they aggregate it together. We've still got layer 3 as the network layer, layer 4 as the transport layer, and really layers 5, 6, 7 are referred to as those data layers themselves. So that is what the OSI stack actually is. But what is a VLAN? What are the benefits? Where does it actually reside in this OSI or TCP/IP stack? So I've just cleaned the screen a little bit. Now when we have layer 2 communications, what Ethernet uses is MAC addressing, or media access control. And this is actually what a MAC address, just for example, actually looks like. You've got 3 bytes which is assigned from the IEEE, so the IEEE, or the Institute of Electrical and Electronics Engineering, if I remember correctly, will assign an organisation the first half of their MAC address. So the IEEE says this is the first half of your MAC address that you're going to put onto your network interface cards, or NICs. What the other 3 bytes of the 6-byte header actually consists of is vendor assigned. So every vendor will then populate the last half of that MAC address and say, right, here's the final 3 bytes of the NIC, of the network interface card. Now you've obviously got a source and a destination, and in a switch there will be a MAC address table. MAC table. Now depending on, yes, vendor, but also on hardware, i.e. is it a low cost switch or is it a very, very expensive switch, these are really going to be able to store a different amount of MAC addresses. The point of why I'm saying this is because if you've got more hosts, more users, more servers, etc., connected to that switch, then that MAC address can actually support, then that switch is going to start discarding, dropping MAC addresses out of its table, and it's a first in first out kind of perspective, and also there's a time associated to it as well. But when we've got our hosts here, and if we're just going to concentrate on this network here, so we've got hosts 2, 3 and 4. We don't worry about the VLANs right now, but when they first connect to this switch, it's a router, but we'll just use a switch for example. What will happen is they don't initially know who's connected to the network, i.e. where is, from host 2's perspective, where is host 3, where is host 4. And so what they'll do is they will send out an ARP request, address resolution protocol. They have in here a specific knowledge of host 3 or host 4's IP address, and they want to know what is the MAC address associated to it. And so let's say host 2 wants to communicate to host 4. It knows its IP address. Host 2 knows that, hey, I need to get to 192.168. Actually, you use host 3. Hey, I want to get from host 2 to host 3. I want to see what's the MAC address of 192.168.10.3. Now, what the MAC will do, the switch with the MAC table, is it will actually queries the ARP table. And in here, we've got an IP to MAC address binding. Host 3 has this IP and this MAC. Host 4 has this IP and this MAC. So initially the switch can respond very quickly to host 2's ARP request with an ARP reply. But what happens if the switch doesn't know where host 3 is, has no knowledge of host 3's existence, because maybe host 3 is connected for the first time as well? Well, what happens then is the switch will send out in all directions to all connected ports which are up the ARP request. It basically floods the whole LAN, local area network, with the ARP request saying, are you this address? And when that host with that MAC address responds to that ARP request, that switch will then update its MAC address table to say, on this port I've got this MAC address connected to me. on this port, and I'll now let the originator know that the destination MAC address to this IP is, well, whatever that address actually might be. So that's generally how it works. My big point here is that Ethernet is a flood and learn. Okay, if there's one big point I want you to take away, there is that the switch will broadcast in that local area network. It will broadcast out all connected interfaces which are up that frame, that ARP request, and we will get the response back, update its MAC address table, update the ARP table as well, and at the same time inform the originator of the ARP request, this is the MAC address you're actually looking for. So how does this actually relate to VLANs? Well, VLANs actually are a virtual local area network, i.e. we can actually segment a switch into virtual LANs. So within this switch here, we've actually segmented it into two different VLANs, VLAN 20 and VLAN 10. VLAN 10 has two hosts, VLAN 20 has one host. And what that basically does is it allows us to control that broadcast storm. So instead of that switch sending all those ARP requests out of all interfaces for that one big giant VLAN, which by the way is default whenever you start up a new switch or multi-layer switch, all interfaces are in that default VLAN by default. But by assigning a virtual LAN to an interface and sub-interface or unit in the Juniper Junos world, we are controlling that broadcast storm. We're minimizing it. Yes, Ethernet is always going to use this flood and learn, but we're not having this massive broadcast going out all the interfaces and units themselves. But what it also allows is a certain amount of priority. So what you can do here, coming back to those real-time and non-real-time services at TCP layer, UDP respectively, i.e. layer 4, the transport layer, is you can assign a certain amount of priority at layer 2. So you can assign, because this is 3 bits, we have 0 to 7. We have a 8 value header. Because 0 is actually a number. So 0 being you have got no priority. So this might be absolutely best effort traffic, whereas 7 is critical traffic. So this would be network management. This would be absolutely critical traffic that must not have any other services or traffic at layer 2 prioritized over it. And you can also apply a certain amount of security. It is basic though, because here we just basically use a VLAN ID to segment traffic away from each other. It's not what I'd really call a firewall feature. But that is what a VLAN is. But why do we actually need, and how do we actually configure this on a Juniper Junos device? Well, first let's cover this aspect of access. What is an access interface? The way I always remember this is it's any device which is actually connecting to that wired switch, to that wired network. It's an access interface. So we can actually see here we've got these hosts here and over here, can't forget this guy, that are connected via all these interfaces, these wired connections to that switch and to this MX router here, which I'm going to show you how to do as well. But it's an access interface, when the traffic comes in which is untagged, when that switch or multi-layer switch forwards it through its device, it is going to then tag it with a specific VLAN tag, i.e. the identifier. So as I said, we use identifiers to identify different VLAN tags, different VLANs, i.e. different broadcast domains. So that is what an access interface is. But if there was a link between this VEX switch here and this VMX router here, you can actually see there's VLAN 10 over here, and we've got these guys in VLAN 10 over here. Without this link, obviously that's not going to work, i.e. that physical layer and all the lovely protocols on top of it. However, what we do want to add over here, over this link, is VLAN 10 to allow the VLAN 10 to pass from here all the way over to it, and obviously vice versa. And we also maybe want to add VLAN 20 onto here as well. Really, I don't know what happened there, but VLAN 20 onto there as well, so that VLAN 20, the host in VLAN 20, can communicate to 192.168.10.1, i.e. this host, this guy, all the way over here. And that is what a trunk, I don't know what is happening there. There we go, I sorted out my tool, it's just a little bit of playing about. But that's what we refer to as a trunk interface, i.e. we want to add all these tags onto this trunk to go from this switch to another switch, up to a router to allow inter VLAN communication. You can do that on a switch, a multi-layer switch. We'll come on to that in a future video, but that's a trunk basically. And so what the big thing to take away from here is that we do have to assign the right interface mode to the right interface. So these interfaces here need to be set as a access interface, whereas these interfaces over here need to be configured as a trunk to go from all the way over here and back and forth. And this is what the VLAN header actually looks like. As we've already covered, we have 3 bits to a VLAN priority, i.e. is it low, no priority, is it some priority, or is it all the way up to 7, because you have 3 bits which allows for 8 different combinations, 2, 4, 8, 3 bits. So that is the P bit or priority value. We also have a drop eligible or canonical eligible indicator or DEI-CEI. The CFI is typically not used these days from my understanding. The DEI might be used depending on that TPID or tag protocol identifier. I know this is a bit more advanced, but it's still good information. VLAN ID allows the separation of one broadcast domain over another broadcast domain. One set of users in their own private network compared to another set of users in a different private network, segmented by VLAN IDs. And the TPID basically states what type of VLAN am I. Am I C VLAN, S VLAN, or E VLAN? C being customer VLAN. So when we talk about service providers, they will enable and configure their edge routers to allow, yes, certain C tags coming in, which would be the end users themselves, but then they would also then assign an S tag. So a service provider will have X amount of their end customers, and they obviously want to keep all their businesses users away from one each other for obvious reasons. So they will then provide an S tag to go over their network to segment their customers away from each other. And E is the enterprise VLAN itself, which is more for carrier networks. But how do you actually configure this on a Juniper Junos device? So let's first show you how we configure a VLAN on a Juniper Junos device, specifically a VEX switch. So let's go into configure mode. Well, actually, if I just do, before I do configure mode, just show you one command that you can run, show VLANs brief. Here we can actually see straight away what VLANs we have. So we got the default VLAN with the tag of 1. So we don't have, as you can see, any other VLANs configured for this switch. So let's go into configure mode, and what I want to do, that's fine. So let's do set VLANs, and now I need to give it a name. So I'm going to call VLAN 10 just V10, and I want to give it a specific VLAN ID of 10 itself. Now what I do want to do as well is actually configure a particular gateway. So you can see here VLAN 10 gateway 192.168.10.254. So what do we do to actually configure that? Well, if I hit question mark, this is what you need, the layer 3 interface or L3 interface. So if I do L3 interface, hit question mark again, it's just going to say define the interface itself. Now on the VEX and QFX devices, and it's the same on the MX devices, i.e. for Junos, it is IRB or integrated routed and bridging interfaces. In the Cisco world, I think they call them SVIs, and certain to some aspect I think we also did in earlier software releases as well. But here we define IRB.10. And if I just quickly do show VLANs, you can see I've now configured it. But that's the VLAN configured. We haven't committed this configuration yet, but we haven't configured actually any interfaces for this VLAN itself. That's what we actually need to do next. So we can see that VLAN 10 is for So over here is for the jncis-ent interface. So let's do set interfaces jncis-ent1, and it should do the .0 family Ethernet switching. Now we need this to be an access interface because we're allowing that host access into the wired network. So let's do interface mode, hit question mark, and now you can see, is it trunk or access? Obviously we want it to be access. How do we assign VLAN 10 to this jncis-ent1 interface? Well, here we just write VLAN members and hit question mark again. You can't see V10 because I haven't committed the configuration yet, but if I just do V10, because we can see it's actually just up here, V10, and do show interfaces jncis-ent1, and we can see that it is configured. What we haven't done yet is actually built the IRB interface. By that, what I mean is we've configured the VLAN 10 to point to that layer 3 interface IRB 10. We've configured VLAN 10 to be on the jncis-ent1 interface using VLAN 10, but we haven't built the interface for IRB 10. So if I do show interfaces IRB, it comes back with absolutely nothing. So that is the gateway for hosts 2, well, host 1 I should say, but also 2 and 3 on the other side on the MX router. So we have to configure that layer 3 interface, that gateway. So let's do set interfaces IRB.10 family INET address 192.168.10.254/24. Let's do show interfaces IRB, and now we can see it's configured there. Now let's do a quick commit check, and now that it has committed successfully, if I now do a ping, let's actually see if I can ping. I can't actually remember if I configured the IP on this host. We'll see in just a second. But let's do a run show VLANs brief. Let's actually make sure it's not committed. That is a worry. This is the good old, it's fairly new software. So let me do that commit once again. And there we go. Second time lucky. The VEX software it's very new, so there's still a few little bugs in the system, but it's okay, we can work with it. But you can see on the second time round, don't worry, it's all good. We can actually see VLAN 10 has been built and it is assigned to the jncis-ent1 interface itself. I haven't said that, it might be my server, but that's great. So let's now do a run ping 192.168.10.1. Can I ping the host? And I can. I did configure that IP. That is great. So now that gateway can configure, or the EX switch I should say, can ping 192.168.10.1. Can the host, however, ping the gateway? So let's do on the host ping 192.168.10.254, and there you go. You can see that the host can now ping the gateway, the IRB.10 interface. So let's recap. How do you do this? How do you configure a VLAN on a VEX or even a VQFX switch? The configurations are very identical, if not the same. So first we have to configure the VLAN. So you give the VLAN a name using the set command, give it an ID, and if you want that VLAN to have a gateway, you don't have to do this, but you need to define a layer 3 interface, i.e. that IRB. Next step from there, I didn't do this, but this would be more logical, is to actually build that IRB interface itself, i.e. do the set interfaces IRB.10 family INET address, etc, etc, etc. Then what you need to do, because we've built the VLAN, and as we did, is actually assign that VLAN to an actual interface. So as I done here, let me do the .0. Oh, I'm doing set instead of show, so let's do show interfaces jncis-ent. Here we go. So I then, yes, built the interface Ethernet switch, which means layer 2. Again, Ethernet is a layer 2 communication. It's a layer 2 protocol technology, however you want to call it. Using the interface mode of access with VLAN members 10, you can only have one VLAN associated to an access interface. You can't have 2, 3 plus. It's not going to work. You do that with trunk interfaces when you want to carry from point to point a certain number of VLAN tags and a default VLAN, or native VLAN I should say, which we'll come on to in a later video. But that's how we do it on a VEX and VQFX switch, or even the physical devices themselves. It is, however, a little bit more different when we talk about the MX routers, which is why I've built these guys here, because it is different. So how do we configure this on MX devices? The reason why I'm showing this is because it is slightly different to that on a EX and even a QFX switch. Some things that are the same, however, is how we configure the IRB interface. So we still configure the IRB interface, so set interface IRB10 in family INET address 192.168.10.254/24. We still need to configure the interfaces to be part of that VLAN as well. So if we look over here, we can actually see jncis-ent and jncis-ent are part of VLAN 10. So let's do set interfaces jncis-ent family bridge. This is the difference here, one of the differences. On the QFX and EX switches, this would be family Ethernet switching. Here it's family bridge. Different name, same functionality. But family bridge, and now I need to say this is interface mode access with VLAN ID of 10. And I need to do the same for the jncis-ent interface as well. Now in terms of configuring and building a VLAN, that's as far as the similarities really go between the MX routers and the EX or QFX switches. The reason why I say that is because if I do edit VLANs, you can see that Junos really doesn't like that. We don't have a separate Junos tree branch to configure VLANs. This is actually all done in a area called bridge domain. So if I do set bridge domains, just give it a name, bridge, and I now can configure this to point out that IRB interface, IRB10, that we just configured. But if I hit question mark, you can actually see it doesn't say L3 interface like we saw on the VEX switch and on the QFX switches. But what we do have is routing interface. So if I define routing interface IRB10, and now if I do edit bridge domains bridge show, we can now see that it's here. It's now saying, oh, you don't have a VLAN tag, but that's fine. That's actually my next point. Here in that bridge domain called bridge, we can now say set VLAN ID of 10. If I do quick show, you can see that message has disappeared. So if I do top show interfaces jncis-ent, just for example, we can see here, and it's the same for jncis-ent, we're saying for unit 0, I want this to be switched, i.e. bridged, access interface using VLAN ID of 10. Here we're saying in this bridge I want to have the gateway that's assigned to the IRB 10 with VLAN ID 10, and I also need to configure the I'm trying to find it but I can't find it. So let's do set interface jncis-ent interface as well. It's because I haven't configured it yet. So let's do 2.0 and let's do 3.0. Let's do show. And actually they're not needed, that's why I left them out. So let's do delete interface jncis-ent. That's why. See, the differences will catch you out. So let's do jncis-ent, let's do show. So that actually does make perfect sense, because here for that bridge we're saying, well, for this bridge we're using VLAN ID of 10. We're using routing interface of IRB10. But for the interfaces themselves, top show interfaces jncis-ent, we're saying, well, VLAN ID 10 is assigned as an access interface for this particular interface jncis-ent and jncis-ent, which is why we don't need to define it in the bridge domain itself. So even I got caught out there. So as you can see, there are differences between how we do this on a QFX and EX switch and on a MX router. So let me just do a quick commit check on this, and that has passed. So let's now commit this configuration, and that has now built that configuration. So if I now just do a run ping to ping host 2, which is 192.168.10.2, and you can see we could ping host 2. We can also now ping host 3. Can they ping each other? So if I just log on to host 2, let's see if I can ping from host 2 to host 3. Let's do ping 192.168.10.3, and you can see we've got, as such, end-to-end connectivity through that switch. So let's now bring VLAN 20 into it on the MX devices. Now, if I go to edit bridge domains, we've got, if I do it right, show, we've got our command, our configuration for bridge, i.e. VLAN 10. I'm actually just going to rename bridge to V10, just so it makes more sense. So let's do that now, and I'll just give that a quick commit. And let's hit show, and that makes a bit more sense now. So we've got a bridge domain for VLAN 10, and those interfaces pointing to use VLAN 10, obviously access. But we now need to configure VLAN 20. So this is going to be our second bridge domain, and I want this pointing out of routing interface IRB 20 for that gateway, and it is also going to use the VLAN ID of 20. So if I do a show now, you can actually see we've got VLAN 10 and VLAN 20. But we still need to configure the jncis-ent 4 interface, because that's going to host 4, which is using VLAN 20. So let's do jncis-ent 4 family bridge interface mode access VLAN ID of 20. And I also need to do the IRB interface, IRB 20 family inet 192.168.20.254/24. And I forgot to put the address in. Oh, it's getting late now, so family address, and let's now do a quick commit check, and that has passed, and we'll do a commit on that, and that has thus succeeded. Can VMX ping the host 4? So let's do a run ping 192.168.20.4, and you can actually see we can. So let's just log on to host 4 and see what can we actually ping the gateway, because I didn't define a source ping there, i.e. the source of 192.168.20.254. So let's do ping 192.168.20.254, and you can see we can. Can we actually ping another host though, i.e. host 2 on VLAN 10? So let's do ping 192.168.10.2, and you can see we actually can. And that is really where I want to finish in terms of points. With Junos devices, inter VLAN routing is just enabled by default. So as you can see, if you want to go from VLAN 10 to 20 or 20 to back to 10 for those ICMP responses, ping responses, that is automatically allowed. So if you want to do any firewall policies, filter out on who can communicate to who and who you want to prevent and block and what applications, you can of course do that using firewall policies and then input them as a filter, whether it be on the interface, on the VLAN, or on the layer 3 interface itself. Obviously it's going to be slightly different configurations, but that will be a future video. So that's the end of this video on the OSI or TCP/IP basics, the layering, the different names of those layers, what type of information you get at those layers, the bits, the bytes, the frames, the packets, the segments, the data, and of course what is a VLAN, a virtual local area network, what's the difference between an access, a trunk, and of course how to configure these on the Juniper Junos devices. So as you can see, it's pitch black here. It doesn't take that long to configure these in real life. Just glorious work for you. But I hope you enjoyed this video. Thanks for watching. If you liked what you saw, please like, subscribe, comment. I love hearing from you guys, and I look forward to showing you the next video. Thanks for watching, and goodbye.